Hi everyone. Today we're going to focus on HTTP 1.0 and we'll see what are the improvements it brought on top of HTTP 0.9 and what are the issues it had. So one of the major improvements of HTTP 1.0 was the introduction of metadata headers. So let's say we have a client and a server, and the client makes a request to the server. So as part of HTTP 1.0 request, our TCP connection is opened, and on this TCP connection, the request is made. Now, whenever the server responds back with a response, on this response, HTTP metadata headers were allowed. Headers such as content type, headers such as content length, they were allowed. Now, as a result of the content type being allowed, the servers were able to send raw bytes of any other file type other than HTML content. And the clients, they would interpret the bytes being provided by the server based on the content type. So let's say if the content type is of image, PNG, JPEG, or if the content type is of type PDF, or if the content type is of type HTML, the clients can easily recognize the content type, and based on the content type, it can interpret the bytes being sent by the server differently, which was not the case in 0.9. It always were sticking to HTML content. Okay, now as a part of content length, the servers would tell the exact length of the response it is sending. Okay, so in the absence of content length, the clients would always wait for this TCP connection to be closed by the server to know that the server has sent all the data it was supposed to send, because the content length was missing. But now with the content length in play, the servers would itself tell that, let's say I'm about to send you 10 bytes. So the clients would stop listening to further data or would not wait for the connection to close once it has listened to 10 bytes, once it has got the response as 10 bytes length. Okay, so this was one of the major improvements on HTTP 1.0, as a result of which your error handling was better, because earlier the connection, whether it dropped due to network congestion or whether the connection was closed because the server was done sending the data, this could not be differentiated. But in HTTP 1.0, it could be differentiated. So the error handling was better. Also, your HTTP 1.0 allowed post requests. So as part of the post request, now your clients could send the data as payload in the request itself. Okay, and also HTTP 1.0 introduced HTTP status code. So when the server is sending the response back right here, it can add the status also. So whether there was a success response, that this response is a success response, or whether there was some errors fetching the response, so or whether there was some resource that was not found, all these status codes could be basically added as part of the response, and so the clients were able to handle the errors in a better way. Okay, and there was some level of caching that was introduced in this particular uh, version of HTTP. So let's say when you have a client and when you have a server, okay, it is not always true that the client always connects to directly to the server. So let's say your client would be connecting to some internet service providers servers, and the internet service providers would be connecting to CDNs, and the CDNs would be connecting to further intermediate servers, and then the final request would fall onto your destination server. Now, what happens is, let's say you are accessing google.com, and the google.com, when you open google.com, there are icons that get displayed. So these images can be cached at CDNs or internet service providers, because these images don't really change over time much. Okay, so as part of HTTP 1.0, two options were provided. One was an expire time, and the other one was if not modified, if not modified since. Now, what happens is, if an expire time was provided, so the servers would, while sending any image, would tell the will add in the response that the expire time for this particular response is, let's say, 8 a.m. Okay, so after 8 a.m., whichever whosoever is accessing this resource again will not use the cache, but will actually come to the server to get the actual data. Otherwise, if before 8 a.m., anyone can take this cache and use this resource from the cached contents at the internet service provider level or at the CDNs level. Okay, and these guys would cache such contents wherever the expire was provided. Okay, and if the clients, multiple clients are accessing the same content again and again, they would actually see if the expire time has not passed. They would give it, instead of making the calls directly instead of making calls from these servers to the actual destination servers, they would give it from their own cache. Okay, now the second one was if not modified since. So in if not modified since, the servers, the intermediary servers would cache the contents, and they would go and when a client would request for the content again, it would go and ask the servers whether you have modified this content after this time. Okay, so if you have not modified this content after this time, I will use my cache, otherwise I will take the data from you. So the servers would respond back not modified. So this would consume very less bandwidth as compared to sending the whole data again and again. Okay, but this again had issues because your different time zones, because of the difference of time zones, your intermediary servers can be on a different time zone and your actual server can be in a different time zone, and the 8 a.m. for this server is actually not 8 a.m. for this server, and there would be inconsistency in the caching. Okay, caching timings. So this was one of the shortcomings. Also, there were security issues in this caching mechanism because you did not differentiate between a public cache and a private cache. What would happen is, let's say I am sending some data. Let's say I am opening Instagram and I have a follower list, and each of the followers are having some content. So let's say each of the followers have posted some pictures and videos which needs to be actually cached at the client's end and not at intermediate servers. So the actual rendering server, which is your Instagram, they would not send whether it's a public cache or a private cache. And instead of being cached at the client's end, it would get cached at internet service providers or CDNs, which would basically be prone to data breaches. And that could be a like privacy issue. Okay. So privacy was one of the concerns in this primitive caching in HTTP 1.0. Now, coming to broadly the other issues that we had. So weak caching, we have already discussed. Every other connection required a separate TCP connection to be opened. So let's say you have 10 different connections to be requests to be made from the same client to the same server. You would end up making 10 different TCP connections, and each TCP connection is basically a three-way handshake that you make. So basically you would consume CPU, and there would be inefficient bandwidth usages that would be there, and lower throughput would be there because every request is having its own TCP connection and they are not sharing the TCP connections. Okay, there was no mandatory host headers. So what do we mean by that? Let's say we have a client, and on client you type in, on a browser you type in google.com to open Google. So as a result, so this is my domain name, that is my google.com. It would do a DNS resolution, and it would resolve to a public IP. Now this public IP is of a server. Okay, now this server is hosting google.com. Okay, now what happens is your request that is flowing into the destination server does not contain your host. It does not contain google.com. In HTTP 1.0, it will not contain google.com. So what would happen as a result of that? Let's say I have a server, and in the server, I am hosting two services. One is google.com and the other one is facebook.com. So with a one public IP, so the gateways would know when the request comes, that whether I have to route it to google.com or facebook.com. But in HTTP 1.0, let's say if I have multiple tabs opened, okay, I have, let's say in a client, I have multiple, in a browser I have multiple tabs open, and from one tab I'm accessing google.com, and on the other tab I'm accessing facebook.com. So the two separate requests would fall on the same IP, but it does not contain whether it's a Facebook request or whether it's a request for Google. So that would result in conflict, because at the gateway level, the request does not contain which host it's accessing for. Okay, so therefore every public IP always could host only one service. Okay, and so the virtual hosting was not allowed as part, because your because your request did not contain the host. Okay, as a result, what happened, your virtual hosting could not happen, so every public IP only resolved to one particular service. Okay, one host. Okay, we know that IPv4 addresses are limited. Okay, it's basically a 32 bit address, so it's like 2 to the power 32, which is around 4 billion 4 billion IPv4 addresses we have. And as a result, what happened was, this was not meant to scale, because your IPv4 exhaustion started happening, because your public IPs could not be shared across multiple resources, because your request did not have that which particular host it needs to access. Okay, so therefore no mandatory header request, no mandatory host header was an issue. Now, what happened during no chunked encoding? So let's say your client is there and it made a request on HTTP 1.0 to the server. Okay, now the server will respond back, and we know that content length was provided as part of the metadata. Okay, so as part of the content length, the servers would actually tell the whole content length that it is going to render. Now take an example. Let's say this particular request that the client is accessing, requesting, is a big request. Okay, the response is a big response. Let's say we have 10 MB of response that needs to be sent. Now what would happen is, the server has to generate that 10 MB of response. So what happens is, the server takes some time while generating the response. So what would happen is, let's say your 20% of the response has been generated, but we are waiting for 80% of the response, because we need to fill the content length, because the content length has to be provided. Okay, so the servers would keep on waiting for the whole content to be generated, and then would put in the content length, and then would feed to the client. Okay, this resulted in wasting of increased the latency, because the clients was waiting for your request, although the server was able to generate it partially, but it could only send it once the whole response was as in generated, and this resulted in lower throughputs also. Okay, now if the chunked encoding was in place, what would have happened? Let's say if you only generated 20% of the data, you would send the 20% of the data with the content being marked as chunked. So the clients would know that since it's a chunked response, I am getting it in chunks, and I will keep listening to the TCP connection as more data is to come. Okay, but since chunked responses were not allowed, there was no streaming that was in play, and this clients had to wait for the whole response to be coming at all at once. Okay, so these were broadly the issues of HTTP 1.0. Now in the next video we'll go over HTTP 1.1. Thank you.